So as we saw from the graphs, the exponential functions have the form y equals c times b to the x power, where b and c are real numbers, but b has to be positive. So since c is our y-intercept, if c is positive, the graph points up, and if c is negative, the graph points down. And for the base, if the base is bigger than 1, greater than or equal to 1, then the graph is increasing. But if the base is anything like a fraction, which is any number between 0 and 1, then the graph is decreasing. It is a decreasing function. So as we said earlier, e is actually similar to pi, where it's an irrational number, and it's actually approximately equal to 2.718281, so on and so forth. And so basically that means that here, e is our base, and our y-intercept, which is c, is 1, which means that our y-intercept is 0, 1. And this is growing exponentially larger by 2.71, blah, 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 which is basically e. Because exponential functions bring on exponential equations, we would like to have a form of solving for these equations. So if we ever have an equation that has the form of b to the x power equal to a, we can actually use something called log and rewrite this as log base b of a equal to x. And this gives us a form of figuring out what x is. B to the x power equal to a is actually called exponential form, and log base b of a equal to x is called the logarithmic form. If we take a look at the example, and we want to rewrite 3 to the 4th power equal to 81 in logarithmic form, we can actually rewrite this as log base 3 of 81 equal to 4. And this basically means that you're looking for a base which is 3, and you're thinking 3 to what power gives you 81? Well, that is 4. You can also work backwards. Let's say that the question was asking you to evaluate log base 2 of 16. Then that would mean that you were actually trying to find a number that takes 2, and you're thinking about 2 to what power is equal to 16? Well, we know that 2 to the 4th power is 16, so that must mean that x is equal to 4. Another way that we could have written this is that we have 2 to the x power, and we can write 16 as 2 to the 4th power. Since they have the same base, this also means that x has to be equal to 4. So those are two different ways of solving that. And again, this just came from rewriting the function from logarithmic form to exponential form. And you can set this equal to x if that makes you feel comfortable, but it's also easier to just think of what number, 2 to what power, gives you 16, and that is 4. So let's take a look at another example. If we wanted to evaluate log base 5 of 125, we would basically have to think of 5 raised to what power gives us 125. So think. Let's see. We know that 5 to the 3rd power is 125. So that must mean that this is just equal to 3. If you ever come across a logarithmic function, let's say log of x, that has no base, this actually means that your base is 10. Just like the coefficient of x, where there's an invisible 1 in front of x, there's an invisible 10 whenever the base is not shown. So if there is no base, you can always assume that it's just 10. If we're ever trying to evaluate something where we have log base b of b to the x power, remember that this just means that you have b raised to some power x equal to b to the x. And in this case, well, our answer is just x, because x has to be equal to x, as we can see here. Here in this third example, if we wanted to evaluate what log base b of 1 was, well, b raised to what power is 1? B raised to the 0 power. Anything to the 0 power is 1, so this must be equal to 0. There is something called a natural log. and that's actually log base e of x. And we represent the natural log as ln of x. ln of x basically means the natural log, and it's actually the inverse of e, as we saw before. Let's take a look at a side example. If we wanted to evaluate the log of 0, then that basically means, well, in this case, we have no base, so we can assume that our base is 10. This means that 10 to what power gives us 0. But is there any exponent that you can raise something to that gives us 0? No, right? So then that means that this does not exist. This does not exist, or there is no solution. This means that anything inside the logarithmic function has to be greater than 0. It can't be equal to 0 because there is no x value that can give you that solution. So let's talk about the domains of logarithmic functions. So we know that logarithmic functions can't be negative or 0. So if we wanted to take a look at the domain of the log of x, we know that the inside of the logarithmic function, which is x in right now, that has to be greater than or equal to 0. Sorry, greater than 0. Strictly greater than 0. So our domain is x greater than 0. Or in interval notation, we can write that as 0 to infinity. And if we take a look at the second example, we don't really want to look at the number in front of log. 3 is a number that is just being multiplied to the logarithmic equation. And we'll talk a little more about what the 3 means later on. But for now, we can look at the logarithmic function inside. So inside the logarithmic function, we have 2x plus 8. Since we know that the inside of a logarithmic function has to be greater than 0, to solve for what the domain is, we have to set 2x plus 8 greater than 0. And solving for this, so we can subtract 8 to both sides, and then we're left with 2x is greater than negative 8. If we divide 2 to both sides, we have that x is greater than negative 4. So our domain is greater than any value x that is greater than negative 4. In interval notation, this is just going to be negative 4 to infinity. So taking a look at this third example, we can again see that this has something being added to ln and we also have a negative ln. As we talked about before, ln is just a different way of writing log, but with a base of e. So again, we don't really care about the extra things. All we're really worried about is what is inside the function. In this case, we have x minus 1. So we know that x minus 1, we have to set that greater than 0 in order to find out what the domain is. So let's do that. We have x minus 1 greater than 0, and if we solve for x, we add 1 to both sides, so our x has to be greater than 1. So this is our domain. In interval notation, this is just 1 to infinity.